추석 체크했나요? 보시는 분. 정신인. So we are learning the object detection pipeline, especially we have learned the transformer-based architecture, which is called as the DTR. Okay. So yeah, I will explain this maybe. Okay. I will explain this again. So so usually we input the images into the resonant architecture and we encode it first, okay, as the image feature, and then we involve the encoder and also the decoder. Okay, these two are composing the transformer architecture. And their main mechanism is the attention mechanism, right? And this is called as self, and this is also called as self-attention. But here, we somehow involve the cross-attention mechanism because key and values are from the different module, and also the queries are from the previous output, okay? So this is the cross-attention, but we use the same signal as the input, so we call it as the self-attention. Also here, we are using the same signals as the input, okay? Okay, but one important thing is in object queries, these values are learned during training, okay? I mean, they are updated during training, but during the testing, their values are fixed. Okay, they will not be changed during the testing. Okay, and also they don't have any semantic meanings. Okay, they are updated during training to maximize the scores, the accuracy for the detection task, but they do not have any explicit semantic meaning. For example, image features, they are encoding the images, right? They have some semantic meaning, but these object queries are some floating values that can maximize the performance, but don't have any explicit meaning, okay? So that causes some problem, and some DTR approaches, they try to somehow improve it, okay? And also, from now on, we will learn about this deformable DTR, which is having the faster speed. At the same time, they exhibit better accuracy in object detection task, okay? So limitation of DTR, they are first slow, okay? Their inference and their training both are slow, okay? They are 10 to 20 times slow compared to the fast ICNN. And also, they have some scale problems. So normally, the image features, nowadays, we encode image features in multi-scales. However, if we involve such multi-scaled image features inside the DTR, because DTR already suffers from slow training, and yeah, they suffer from their complexity. So if we involve multi-scale features inside the transformer, it may worsen the complexity, okay? So that's the problem called the scale problem, okay? So the DTR, their performance is limited in detecting the small object, okay? But I mean, in deformable DTR, we optimize DTR's performance. By reducing their complexity, so we can somehow enlarge the feature space into the multi-scale. Okay, so we can solve this by reducing the complexity and involving more scales in the image feature space. Okay, so in deformable DTR, the deformable attention mechanism, which is more optimized attention mechanism, is proposed to relieve the heavy complexity and the slow convergence problem. Okay. So this is the overall architecture of the deformable DTR. So here you can see this is the encoding part, and this is the decoding part. Okay, so decoder, encoder. Here you can see we will involve some multi-scale image features. Okay. Previously, we only involved just one scale feature. Okay. But in the deformable DTR, we can involve multi-scale feature thanks to its reduced time complexity. Okay. And so this is somehow different from previous in the encoder and decoder, we involve the deformable attention mechanism, which is faster than the conventional attention mechanism. Okay, so this is representing that, and we will further detail it later. Anyways, thanks to deformable attention, we can reduce the complexity and can also involve multi-scale features. Okay, that's the deformable DTR. And this is more detailed figure for the pipeline. So we need to define first the reference point. Okay, this is some point. Okay, this is some 2D point. Okay, during the in encoder, we will define the reference point as the all pixels in the feature. Okay, we will use all feature pixels as the reference point. But in the decoder, we don't have any explicit spatial information. So I will show you this. So in encoder, we are given some image feature, right? So we are given some image feature, and this has some spatial meaning, but in object queries, we do not have any spatial meaning as in the input space. It is just some vector learned during the training, okay? So for the encoder, we use some 2D point inside this 2D image feature as the reference point. However, in in these object queries, there are no spatial meaning. So we actually infer some 2D coordinate XY from these object queries, okay? So that's denoted here. So in decoder, the input is object queries, which does not have any spatial meaning. So we actually input object queries, and we apply object queries into the linear layer to infer some XY coordinate, okay? And that is actually used as the reference point. However, in the encoder, we retrieve all the pixels inside the E2D image feature, and actually that every pixels are used as the reference point, okay? That's the first thing here. So in encoder, coordinate of query pixel, that's the reference point. And actually in decoder, we have to infer some reference point, okay? So reference point, P of Q, that is actually some one pixel value in the image, 2D image feature, okay? That's the reference point. And then what we have to do is, and this query feature is actually meaning the feature inside this, okay? So we actually extract some pixel feature, okay? And that is called as the query feature. And from this query feature, X of Q, we have to infer two things, the sampling offset and the attention weight, okay? So actually, this is the attention weight, this is A, and this is the sampling offsets. This is some offset, delta P, okay? And actually, this part are making some values. In this part, by sampling some offsets, we are making some values, okay? We are making some value. And here, this part, by inferring some attention weight, we are actually making this part. So this is the original, the key and query dot production originally in the attention mechanism, and later we also product this value and the result of this afterwards in the attention mechanism, right? But in the deformable DTR, in their deformable attention mechanism, rather than estimating key and queries and dot producting these two, we directly estimate this A. This is the attention weight, okay? So this is the way to calculate the attention weight in the conventional attention mechanism, but maybe K can have n element and query can have n element. Then the calculation of this takes n square complexity, okay? So deformable DTR, they say this is too complex. So from the query feature, instead of calculating this dense operation, they apply just the linear operation on the query feature only. So this can be denoted as this, okay, linear. Instead of having explicit key values having n dimensions, similar to the query dimension, they only involve query dimension and apply linear layer on the queries and estimate this attention directly from only the query values. So instead of involving these two, which may result in this kind of too much complexity, they only involve just one and apply the linear operation on it to make this attention weight, okay? So because of this, the complexity becomes less, okay? So we have attention weight from this part, and also for the values, we also reduce the complexity. So previously in DTR, we need to dot product with all of the neighbors, okay? We have to densely product this value to the attention weight for all the elements. But here in the deformable DTR, we are actually sampled the sampling offset here, right? So we actually sample some of the positions from the center point, okay? And now the attention weights are only produced with some values from their sum of sampled neighbors, okay? So two things are happened here. So values are also sampled and keys are not involved, and only queries are involved with the linear operation. So the complexity becomes far less, okay? So But we have multi-head architecture. Still, we have multi-head things. Okay, so this is the deformable attention with the multi-scales. So this part is for adding for multiple head, and yeah, this is the new formula for the deformable attention. Okay, so this is the from the reference point. We only sample few neighbors for calculating the values. So this can for the remove the complexity. Okay. So this part, when sampling value, we sparsely sample the neighbors, and also for calculating the attention part, we remove the keys. Okay, and we don't need order n square complexity. Okay, and for multiple head, we add them and apply linear operation and get the final output. Okay. So, and also the other part is, in the last part, we need to estimate two things. First is the class probability, and second is the bounding box information. But when estimating bounding boxes, we regard this reference point as the center point. This is kind of becoming the center point, and we estimate only the residuals. I mean, this is the center point, okay? The original reference point is becoming the center point, and we only estimate some residuals regarding this as the center point, and actually by adding them, we calculate the updated bounding box coordinate. Okay, that's the other thing. Okay, and this kind of method is proven effective for improving the accuracy of the bounding box inference. Okay, rather than directly estimating the bounding box coordinate, we regard some known point as the center point, and we only estimate their residuals and actually add them to recalculate the update bounding box coordinate. Okay. That's another trick. Okay. So this is the original. This part is important. So I mean, this is the original attention mechanism. So from the query and key, we calculate from the initial input by applying some linear weight, and then we apply normalization and also apply the softmax, and then product with the values in the dense manner. Okay. This was the original attention mechanism. Okay. However, and also this is the extension of the multi-head attention. Okay, in conventional the transformer-based method. So this M is index for head. Okay, and here we can denote this as this first part, we can regard it as A, okay, attention weight, okay? And this part, we can denote it as the value, okay? And previously, this omega, the K index, this is the samples where these values and this attention weight are calculated, okay? So previously in conventional attention mechanism, this omega is denoting all the element inside the original signal, okay? We densely calculate this product previously, right? And we calculate this for each head and apply each head weight and summing over the multiple head. That was the conventional multi-head attention mechanism, okay? So are you guys following this? Okay. So this is the same formula, right? This is the attention weight, and this is the value. This is the attention weight. And this is the dot product between key and query, right? So this is the conventional multi-head attention, but this is the deformable attention, okay? So deformable actually multi-scale deformable attention. Sorry. This is the deformable attention. Actually, but this is called as deformable attention, but it is already involving the multi-head, right? So this is multi-head deformable attention, okay? The multi-head is actually removed in their name, okay? But here, this part, you can see the difference between these two, okay? So the values are calculated only in the some sampled space. So this part is actually meaning this sampling part, okay? Are you guys understanding this, right? So we calculate the values for only sampled region, and also this A, when calculating this A, the attention weight, we do not involve this key information, but directly estimate this attention weight from the queries itself. By applying only the linear layer on the query, we will calculate this part, okay? And for the sampled point, we calculate this product, okay? So the complexity now becomes far less than this conventional attention mechanism. So when calculating this, we do not involve key. That already reduces the complexity once. And we will calculate this product between values for sparse point. Okay, that further reduces the complexity. And we will apply this for multiple head, okay, same as before. So this is actually involving the multi-head things, okay? So this is the reference point. So you can see in conventional attention mechanism, there was no reference point, but in the deformable attention, we need reference point. And in encoder, this reference point becomes the older feature. But in the decoder, we actually have to infer this reference point from the object queries because there are 300 object queries, right? We have to infer 300 reference point. So reference point, it is inferenced from the each object query, okay? Anyways, we infer this for the deformable detail, okay? And another important thing is this multi-scale deformable attention. So this is denoting multi-scale deformable attention. So you can see another argument here. So previously we only involved the X, which is the one scale feature, but here we will involve multi-scale image feature, okay? So actually there are L number of scales inside this image feature, okay? And L is normally 3, okay? L is 3, so because we are involving this type of image feature, whose L is set as 3, so this time the L is fixed to 3, okay? And what we add in the formula is this. So we apply, and also we slightly change the notation of the X by adding this L, right? So the same mechanism is applied to 3 different scaled features, okay? So are you guys following this? Easy, right? So this is the multi-scale deformable attention, okay? So the attention part, we far reduce the complexity, and we can now extend our features into the multi-scales, right? Okay. So this is the core part in the deformable DTR method, okay? But another thing, which might be, which might be minor, is these two, the iterative bounding box refinement and also the two-stage deformable DTR, okay? So yeah, these two are simple. So in the iterative bounding box refinement, what they are doing is they actually involve multiple layers in the decoder. So here and here and here, these parts are all composed of the deformable attention, okay? Here we have deform attention, and here we have another deformable attention, okay? And from each attention, we can infer the bounding box information, okay? We can infer some bounding box information in the intermediate layers of the decoder, okay? So in the final layer, we, of course, estimate the class and bounding box information, right? However, in the intermediate layers, we can also estimate the bounding box information, okay? So this figure is showing that. So from the layer I and layer I plus 1, we can estimate the bounding box from each layers of the decoder, okay? So from I minus 1 layer, we can estimate some bounding boxes. And also from the I layer, we can estimate some bounding box. And for the I plus 1 layer, we can also predict some bounding boxes, okay? We can independently estimate them, but here what they want to do is they actually relate the intermediate bounding boxes they wanted to relate these I minus 1 bounding boxes with the I's bounding boxes to maybe improve the previous bounding box. So in the I's bounding box, they only infer the residuals compared to this I minus 1's prediction. So, I mean, in that way, they expected to improve the previous layers bounding box information, okay? So actually, they designed the decoder layers are refining the previous layers bounding box estimation like this. So this is the bounding box estimated from previous layer. And this sigma is denoting the nonlinear or nonlinear operation, right? So previous layers bounding box, they are already applied with the nonlinear layer, right? So we apply first inverse nonlinear operation to the I minus 1's bounding box, and then add the residual, which is predicted in this layer, and then apply nonlinear again to this added values. So this becomes current layers bounding box information, right? And then apply this nonlinear operation on it, okay? So this is the X, Y, width and height, okay? We are, when describing one bounding box, we need 4 values, okay? Width and height, no, X and Y, and width and height, okay? So we need to predict these 4 floating values, okay? Okay, so somehow they formulate this bounding box prediction by updating the previous layer's bounding box information, okay? Are you guys following this? Okay. And another thing is the two-stage deformable DTR algorithm. As I mentioned before, this is the encoder and this is the decoder of the transformer, right? So this part, we input the image feature, okay, and obtain the enhanced image feature here. And this is the denoting the object query, right? And we actually involve the output of the encoder with the object query and output the class and bounding boxes, okay? This is the DETR algorithm. But one problem I raised before was this object queries is not knowing any spatial information, okay? So of course, this does not have any semantic meaning, but more important thing is they don't have any explicit spatial information, okay? Even though the final output is the bounding box information, which requires the spatial information, okay? However, their initial input do not involve any spatial information, and some researchers are saying that because of this, the lack of spatial information inside the object queries, this can potentially slow the convergence of the DETR, okay? So what they added is actually this part. Okay, here they add this part to the decoder input. Okay, but I mean the image feature, this is having some spatial information. Okay, so the encoder part, we have some of the spatial information, but the decoder part, their input do not have any spatial information. So they actually have another module to estimate some information, and they actually added to as the for the decoder input. Okay. So anyway, they add some of the output information of the final output of the encoder in the input of the decoder. That's the two-stage deformable DTR algorithm, okay? So object queries are irrelevant to the input images. They don't know any spatial information, okay? So, but previous object detector, such as the fast RCNN, they already extract some region proposals, right? And that is having some spatial information already in the input space. So motivated by the fact they involve some information outputted from the encoder output as the decoder input. That's the two-stage deformable DTR schemes, okay? So here, they report the accuracy with the 2 more modules. So this is the original deformable DTR algorithm, okay? And this is the algorithm with iterative bounding box refinement. And this is the algorithm with both schemes, okay? And you can see their accuracies are gradually improving, okay? So one important thing is This is the DETR algorithm's performance, and this is the faster RCNN's performance. And you can see the DETR's performance, especially this APS is denoting the accuracy for small object. And this is the accuracy for medium scale object. And this is the accuracy for large object, okay? Compared to fast RCNN, their overall AP are similar or better than fast RCNN, but and also the medium or large scale objects, the DTR performs far better than the fast RCNN, but for the small scale object, DTR performs less than the fast RCNN, okay? So especially these are becoming less than the faster RCNN, okay? But for the medium and large scale object, DTR is performing far better than the fast RCNN, right? But in the deformable DTR, because we involve the multi-scale features, right? So you can see for most of the objects which have various scales, we have better performance than the fast RCNN. And also we have better performance than the DTR, okay? And also you can see this is the training epochs, okay? This is the training epochs. The deformable DTR, they involve far less epochs, right? For example, here for the DTR, we train them for 500 epochs. However, in this, for deformable DTR, we train them for 50 epochs, right? However, we can see the performance of the deformable DTR that is better than original DTR, okay? And of course, it is better than the fast RCNN, okay? So that's the thing we have to feel from this table, okay? And this is the overall epochs, and this is the training curve of the original DTR. However, I mean, when using only 50 epochs, this is the deformable DTR's training curve, and it outperforms the DTR, okay, with less number of epochs during the training, okay? And that is actually thanks for, I mean, it is achieved by the multi-scale deformable attention and also with these two additional skills, okay? So are you guys following this? Okay. Any questions? No? Okay. And another thing is, so this deformable DTR is proposed in ICLR 2001. And also, this paper called as conditional DTR, they pointed out another reasons why the DTRs are slow in convergence, in their convergence during the training, okay? So this is some visualization of the attention in the DTR algorithm, the conventional DTR algorithm, when the model is trained only for 50 epochs. And also this is the visualization of the attention in DTR when the model is trained for 500 epochs. And also this is the attention visualization for their proposed algorithm. Sorry, their proposed algorithm. So this is the ground truth bounding box. And this might be some correct attention, okay, for when model try to estimate the correct bounding box, their attention have to be correct, right? So conditional DTR, when they are converged, their attention mechanism around the bounding box looks like this. And also when DTR is converged after the 500 epochs, the visualization of the attention looks like this. However, when the DTR is trained only for 50 epochs, their attention becomes inaccurate. Okay, it means this visualization means DTR takes a lot of epochs to make its attention close to the ground truth bounding boxes. Okay, so and they are pointed out that this is due to the object queries. Okay, this is the input to the decoder. Okay, especially these object queries are not having any image specific information, especially for the spatial information. Okay, so it is hard to map these object queries to spatial keys, and this causes the slow convergence of the details. Okay, because the decoder input, the object query, do not have any image-specific information, which is the spatial information. So it takes time to make it have the spatial information in the later layers of the decoder. Okay, so the solution might be to give some spatial information to the object queries, right? That is the assumption of this paper. So they try to involve some spatial information in this object query. Okay. So this is the thing what they did. So decoder embedding. This is the original query, object query. You can regard this as the object query. Okay, and we will call this as the content query because it takes some content. Okay, and now we will call this as we will involve another thing called as spatial query. Okay, so the idea inside the conditional DTR is we will actually divide the original queries into two, which is the content query, and the other is the spatial query. Okay. And we will give explicit the spatial information for this spatial query part. Okay, and we will use the original object query for this content query. Okay, that's the thing this conditional DTR proposed. So we will call this content query as CQ. This is the content query, and this PQ, which may be denoting the positional query, maybe. This is actually will denote the spatial query. Okay, and also this key and value. Actually, value, we apply some positional encoding before, right, in the transformer, but value normally does not take it, but the key have to be improved with the positional embedding, right? So this image feature, we will call this as the content key. This is some having some semantic meaning, but have no explicit spatial meaning. But this positional encoding is giving some spatial information. So we will call this as the spatial key. Okay. So anyway, we somehow divide the queries into content query and spatial query. And another thing is in DTR, we may have to make some addition of this content and spatial query, and somehow we have to mix them, right? And if we calculate the dot product between the key and values, then this may have this kind of formula, right? It is too complex. At the same time, the content and positional information, they are interlinked, right? However, in the conditional DTR, we somehow apply some element-wise multiplication between this content and spatial informations. Okay. So somehow this can be achieved by, rather than adding them in the input space, we will concatenate this content and spatial information and will apply this dot product after concatenating the signals. Then we can get this kind of independent signals. Okay. So this is more efficient and can be more clear for the model. Okay. So conditional DTR, we encode, explicitly divide the content and spatial queries and encode it like this. And another thing is, in conditional DTR, we actually enhance the spatial encoding part. Okay. So previously, object queries do not have this kind of explicit mechanism, but in deformable DTR, they add this kind of two-stage approach before. Okay, that's actually, I mean, this part is actually similar to adding some positional encoding to content query, right? However, now we have different modules to encode some of the spatial information for the spatial query. Okay. So this is the initial output. So this is the some object query. F is denoting some object query, and so this S is the reference point actually inferred from the object query. So for the deformable DTR, we also have to infer this reference point from the object queries. So anyway, this reference point is slightly having some spatial information. Actually, this reference point is meaning the 2D point. Okay. So this part is having some spatial information, but previously their encoding was rather implicit. But here we explicitly concat this reference point information with the object queries, and then obtain this PQ, which is the the queries, the positional, the spatial query information. This is meaning the spatial query. Okay. So here we define PQ as the spatial query, right? So spatial queries are now explicitly encoded in this way. Actually following this complex route. Okay. And first, from the reference point, we input it to some nonlinear layer and apply some sinusoidal function. Okay, and this may result in some of the positional encoding vector, which might be called as P of S. And then we apply further transformation by applying this T matrix on the P of S. And that is actually called as our PQ, the content are the spatial query. And T have the special characteristic. I mean, T, normally we apply T matrix to one vector, P of S. We apply some matrix, the multiplication like this, right? But T is some diagonal matrix and have only entries in this part, okay? So it is actually extracting some diagonal diagonal element only, and that is actually called as lambda q, and actually can be represented like this. So element wisely multiply lambda q with the p of s. Okay. So anyway, by applying this, we further transform this original positional encoding vector. Okay. So anyways, by involving this kind of complex operation, we generate some of the spatial information explicitly from the object query. Okay, that is happening here, right? So 2D encode embedding this part, from the object queries, this S is obtained by applying some linear layer and also applying some sigmoid and positional embedding. P of S is obtained, and this is the T matrix, and then we can get this P of Q. So this is denoting this complex operation, okay? Anyway, you don't need to memorize all the, exact operations, but you can just feel that they try to involve more complex way to encode the spatial information from the object queries, okay? And what they are insisting is from the backbones, when they involve this kind of spatial queries, and to make it as the conditional DTR, their performance are becoming better. Okay, so DTR, they originally require 500 epochs. Okay, and also if they involve only 50 epochs, then their accuracy, their AP, becomes far less than the full converged model, right? However, in conditional DTR, even though they train them for like 50 epochs, this is far better than original DTR, okay? But becoming slightly less than the original DTR trained for 500 epochs, given some different models, right? However, if they train them with few more epochs, then it performs better than the DTR with 500 epochs. Okay. So all of these are because of this fact. Okay, they are actually validating this fact. So the reason why DTR takes a lot of epochs during the training might be because the object queries are not having any spatial information, and it is hard to map such object queries lacking the spatial information to infer some bounding boxes, which requires the spatial information, okay? And it is causing the slow convergence of DTR, so they try to involve complex mechanism to encode the spatial information inside the object queries, right? And then given small number of epochs, they can obtain better performance than the DTR. And it somehow experimentally proves that that was the reason, right? The object queries lacking of spatial information was the reason for slow convergence, right? So this is important. Are you guys following this? Okay. And there was another paper published in ICLR 2022. And this paper is saying that this is the DTR algorithm's attention visualization, and this is the conditional DTR's attention visualization, and this is their proposed attention visualization. So you can see A, which is the original DTR's attention visualization, they are unconstrained and having too small or too big attention, okay? this is not very informative. And B, which denotes the conditional DTR's attention. This is more focused on object, maybe, but it is rather like Gaussians, right? So they are having similar scales to in the direction of X and Y, right? And object scales is not normally considered in these attention things. So that detail, the authors are insisting that they need to encode the attention in this way. So they want to encode the attention non-Gaussian way, having some different scales to X and Y axis. And also they want to achieve more sharp attentions, okay? So maybe later, maybe Wednesday, we will see what they did for this, and then also learn about DNDTR and DNO afterwards. Okay. Okay, thank you. Let's finish here.